In this lesson, we're going to learn how to rationalize the denominator, and we're going to focus on denominators that contain square roots. We're going to need to be very familiar with perfect squares. So for our reference on this first page here, I've listed some of the most common numbers that are perfect squares and some common examples of variable expressions that are perfect squares. We made a very similar list in my 6.3 video. Now, in this video, we're going to learn how to rationalize the denominator of a fraction. What does it mean to rationalize the denominator of a fraction? To rationalize the denominator, you must rewrite the fraction so that there is no radical in the denominator. In mathematics, we don't like to have radicals in the denominator. So, to rationalize the denominator simply means that you're rewriting the problem so that there is no radical in the denominator. In this video, we're going to learn how to rationalize a denominator that contains a square root. So all of the problems in this video will involve square roots. So if you're asked to rationalize a denominator, that means that you're supposed to rewrite the problem so that there is no radical in the denominator. And to do that, we just need to follow these 3 steps. Step 1, as it says here, we need to simplify any radicals if possible. Can this square root be simplified? 5 is not a perfect square, and there are no perfect squares that multiply evenly into 5. So that means that this square root cannot be simplified. So I've just put a check mark next to step 1. We checked, but this radical can't be simplified. For step 2, as it says here, we want to multiply the numerator and denominator by the square root that appears in the denominator. I've started by copying down this exact original problem here. Now we need to rationalize the denominator, meaning that we need to get rid of the square root in the denominator. And there's a nice, easy trick. To get rid of a square root in the denominator, we just multiply the numerator and denominator by that square root in the denominator. So the square root in the denominator is the square root of 5, so we're going to multiply the denominator by that exact square root, the square root of 5. And if we multiply the denominator by the square root of 5, we also have to multiply the numerator by the square root of 5. Now, what does that leave us with? 1 times the square root of 5 gives us the square root of 5. And we learned in my 6.4 video that when you multiply 2 identical square roots, the answer is just the radicand, which is 5 in this case. So the square root of 5 times the square root of 5 is just 5. And look, we have now rationalized the denominator, meaning that we've gotten rid of the radical in the denominator. For step 3, you want to make sure that you've written your final answer in simplified form. We cannot simplify this any further, so this is our final answer. Notice here, because this could be confusing, in mathematics, we're typically okay with having radicals in the numerator. But mathematicians do not like having radicals in the denominator. So for your final answer, make sure there is no radical in the denominator. But if you have a radical in the numerator, that is okay. And another important note is that this expression here is equivalent to this expression here. If you converted this to a decimal and then converted this to a decimal, you'll find that they equal the exact same decimal because these expressions are equivalent. And the reason these are equivalent is because when we multiplied the top and the bottom by the square root of 5, we really just multiplied by 1. And when you multiply by 1, you don't change the value of your expression. Now, before we move on, I want to provide a brief explanation of why mathematicians do not like to have radicals in the denominator. Here I'm going to show you one reason why we'd like to get rid of radicals in the denominator. This is the exact expression we saw in problem 1. And we rationalized the denominator, which means we rewrote it without the square root in the denominator. When might this be helpful? Well, let's suppose you were given the problem shown here. It would be really difficult to add these expressions by hand as they're written. But you'll see that once we rationalize this denominator, it becomes much easier to compute this by hand. Again, this is the exact problem we just worked through on the first page. We rationalized this denominator, and our answer was this expression here. So once you've rationalized this denominator, in other words, you've written it so that there's no radical in the denominator, now it becomes much easier to compute this sum. We could add a 1 here, and that doesn't change anything. And then I'm just going to slightly rewrite this by pulling the 1/5 out front. And I'm going to do the same thing here. I'm just going to pull this 2/5 out front. Now we can add these by hand. In my 6.4 video, we learned that you can add radicals if they are like radicals. These are like radicals since they have the same radical base. Their radical base is the square root of 5. So to add these radicals, we keep the radical base, which is the square root of 5, and we add their coefficients. 1/5 plus 2/5 will give us 3/5. So we can see that rationalizing the denominator is not just a silly rule. There's reasoning behind it. One of the reasons we like to rewrite problems so that there's no radical in the denominator is because it can make mathematical calculations much easier to perform. Let's try the next problem together. So we want to rationalize this denominator, which means we want to rewrite it without the square root in the denominator. Step 1, we want to simplify any radicals if possible. Well, let's see, in the numerator we have the square root of 6. 6 is not a perfect square, and there are no perfect squares other than 1 that multiply evenly into 6. So this radical cannot be simplified, and same with the square root of 3. 3 is not a perfect square, and there are no perfect squares other than 1 that multiply evenly into 3. So neither of these radicals can be simplified, so I've just put a check mark next to step 1. For step 2, we're going to multiply to get rid of the radical in the denominator. I've started by copying down this exact original expression here. Now remember, we're okay with having radicals in the numerator, but we do not want radicals in the denominator. So to get rid of the radical in the denominator, all we have to do is multiply the numerator and the denominator by that exact radical that you see in the denominator. So the radical in the denominator is the square root of 3, so we're going to multiply the numerator and the denominator by the square root of 3. In chapter 6.3, we learned the product property of radicals. And the product property of radicals says that when you multiply two radicals that have the same index, you can just combine that multiplication underneath one radical symbol. So that would give us the square root of 6 times 3. Now let's look at the denominator. Remember, when you're multiplying, you multiply like quantities. So we multiply any coefficients together and we multiply any radicals together. There's no coefficient here other than 5, so there's nothing to multiply the 5 by, so we'll leave it as is. But we want to multiply the radicals together. You could use the product property of radicals to multiply these two radicals like we did up here, but instead we can use a shortcut. Whenever you multiply two identical square roots, the answer is just the radicand. So the square root of 3 times the square root of 3 just gives us 3. And if we simplify, this will give us the square root of 18, and 5 times 3 will give us 15. Now we've completed step 2. We've gotten rid of the square root in the denominator. For our last step, we want to simplify any radicals if possible and reduce any fractions if possible. I'm going to start by copying this expression right here. Whenever you have a radical for your final answer, you always want to check to see if that radical can be simplified. For an introduction and detailed explanation of how to simplify radicals, please watch my 6.3 video. To simplify the square root, first we ask ourselves, is 18 a perfect square? If you look at our list of perfect squares, either on page 1 of our worksheet here, or we also made that same list in our 6.3 worksheet, you'll find that 18 is not a perfect square. So since 18 is not a perfect square, we need to find the largest perfect square that multiplies evenly into 18. That would be 9. So let's rewrite 18 as 9 times 2. Now 9 is our largest perfect square, so we need to write it as some quantity squared. So I've just rewritten 9 as 3 squared. Now we've learned when you have a square root, anything underneath the radical that has a square for an exponent can be pulled out of the radical. So we can pull this 3 out of the radical, and that will leave us with the 3 that we're pulling out. The 2 stays underneath the square root, and in the denominator we still have 15. Now we've focused on the numerator here, and we've simplified the square root in the numerator. Now in step 3 we also want to check to see if we can reduce any fractions. Notice 3/15 can be reduced to 1/5. And when the coefficient of your radical is a 1, you don't need to write it. So for our final answer, we can write the square root of 2 over 5. Let's take a look at this example over here. For step one, we simplify any radicals if possible. Now, for step one, it might be difficult to figure out how to simplify these radicals, and it also might not be clear that there is, in fact, a radical in the denominator. So, in step one, let's start with the quotient property of radicals. We learned the quotient property of radicals in my 6.3 video. The quotient property of radicals says if you're dividing two quantities underneath a radical symbol, you can break that division apart into two separate radicals. So that would give us the square root of 8 divided by the square root of 21p. Now we can see that we do in fact have a radical in the denominator, and it'll also be easier to simplify these radicals because we can just focus on the radical in the numerator and focus on the radical in the denominator. To start, the square root of 8 can be simplified. 8 is not a perfect square, so we need to find the largest perfect square that multiplies evenly into 8, and that would be 4. So let's rewrite 8 as 4 times 2. What about the denominator? Can we simplify the square root of 21p? Well, 21 is not a perfect square, and there are no perfect squares other than 1 that multiply evenly into 21. P is also not a perfect square, and there are no perfect squares that multiply evenly into p. So the square root in the denominator cannot be simplified, so I'm just going to copy it over for now. Now let's focus back on this radical in the numerator. Once you identify your largest perfect square, we want to rewrite that as some quantity squared. So I've rewritten 4 as 2 squared. Since this is a square root, anything underneath the radical that has a 2 for an exponent, we can pull out of the radical. So I'm going to pull this 2 out of the radical, and underneath the square root, we'll still have this 2. And then I'm just going to copy over this denominator. Now we've completed step 1. We've simplified the square root in the numerator, and the square root in the denominator could not be simplified. Step 2, we're going to multiply to get rid of this square root in the denominator. I'm going to start by copying this exact expression over here. To rationalize this denominator, in other words, to get rid of this square root in the denominator, we multiply the numerator and denominator by this exact square root that we see in the denominator. So we're going to multiply the numerator and the denominator by the square root of 21p. And let's see, remember when you're multiplying, you multiply like quantities. So you multiply any coefficients together and you multiply any radicals. 2 is the only coefficient, so there's nothing to multiply the 2 by. So let's just carry over the 2. Now we multiply the radicals, and we'll use the product property of radicals here. If you're multiplying two square roots, you can combine that multiplication underneath one square root symbol. So that will give us the square root of 2 times 21p. Now, when we're multiplying the radicals in the denominator, we could use the product property of radicals, like we did up here, or we could use our shortcut. Since we're multiplying two identical square roots, the answer is just the radicand. In other words, the square root of 21p times the square root of 21p is just 21p. Now let's take 2 times 21p to get 42p, and now we've completed step 2. In step 2, we're getting rid of the square root in the denominator. For step 3, you just want to check to see if you can simplify any further. Can we simplify any of the radicals? Well, let's see. 42 is not a perfect square, and there are no perfect squares other than 1 that multiply evenly into 42. Same with p. P is not a perfect square, and there are no perfect squares that multiply evenly into p. So this radical can't be simplified any further. We also want to check to see if we can reduce any fractions. Can 2 over 21 be reduced? No, it can't. So that means that this is our final, fully simplified answer. Notice we've rationalized the denominator because there is no square root in the denominator. Let's take a look at a few more examples of rationalizing the denominator. Now we're going to follow the same 3 steps for each of these problems. For step 1, we're going to simplify any radicals if possible. Now, a common question often comes up. Do we actually have to do step 1? Do we have to simplify the radicals in the beginning? To rationalize this denominator, can we just right away multiply the numerator and denominator by this radical that we see in the denominator? Yes, you can. That's another correct way to solve the problem. You technically don't have to simplify the radicals at first, but if you do it this way without simplifying, you're going to end up with bigger numbers that can sometimes be a little bit more difficult to deal with. And you'll have to simplify in the end, but you're going to be dealing with bigger numbers when you're simplifying in the end. So I like to simplify in the beginning because that makes our numbers nice and small and often easier to work with. I'm going to start by copying down our original problem here. So let's see if we can simplify either of these radicals. Since these are square roots, we're looking for perfect squares. 7 is not a perfect square, and there are no perfect squares other than one that multiply evenly into 7. So the square root of 7 cannot be simplified. Let's check this radical. 32 is not a perfect square. The largest perfect square that multiplies evenly into 32 is 16. So let's rewrite 32 as 16 times 2. Now we need to rewrite 16 as some quantity squared. So I've written 16 as 4 squared. Now, since this is a square root, anything underneath a radical that has a 2 for an exponent can be pulled out of the radical. So I'm leaving our numerator exactly as is. And in the denominator, we'll pull this 4 out of the radical. And all that we'll have left underneath the radical is the 2. Now we've simplified the radicals in step 1. The square root of 7 couldn't be simplified, but we simplified the square root of 32 to 4 square root of 2. But now I also see that we can simplify this a little bit further because the fraction negative 10 fourths can be reduced to negative 5 halves. So now we've simplified the original problem as much as we can at this point. That's going to make our numbers nice and small and easier to work with. For step 2, we're going to multiply to get rid of that square root in the denominator. I'm going to start by just copying this expression over here. To get rid of this radical in the denominator, we multiply the numerator and the denominator by that exact radical that we see in the denominator. Notice you don't need to multiply by the coefficient. You only need to multiply by the square root in the denominator. Now when we multiply any coefficients. Well, there's no other coefficient to multiply the negative 5 by, so we'll leave the negative 5. And we multiply the radicals. To multiply the square root of 7 times the square root of 2, we'll use the product property of radicals, which says we can combine that multiplication underneath one radical symbol. So that will give us the square root of 7 times 2. Then in the denominator, when we're multiplying radical expressions, we multiply any coefficients. Well, there's no other coefficient here other than the 2, so we'll just carry over the 2. And then we multiply the radicals. Now we could use the product property of radicals, like we did here, or we can use our shortcut. Since we're multiplying two identical square roots, the square root of 2 times the square root of 2 is just equal to 2. And let's see, in the numerator, we'll have negative 5, square root of 14, and in the denominator, 2 times 2 will give us 4. And I just noticed that this negative in the original problem was written out front, and I moved it to the numerator. You could have left it out front if you wanted to. And for your final answer, you can put the negative in the numerator or out front. Either way is correct. Now that we've rationalized the denominator, in other words, we've rewritten our problem so that there's no radical in the denominator, for step 3, we just want to check to make sure we can't simplify any further. Check to see if you can simplify the radicals. Well, if we look at the square root of 14, 14 is not a perfect square, and there's no perfect squares other than one that multiply evenly into 14. So the square root of 14 cannot be simplified. And you also want to check to see if you can reduce any fractions. The fraction negative 5 fourths cannot be reduced any further. So this is our final answer. Let's take a look at this example here. For step 1, we want to simplify any radicals if possible. So I'm going to start by copying this original problem here. And can we simplify this square root in the denominator? 20 is not a perfect square. So we need to find the largest perfect square that multiplies evenly into 20. That would be 4. So let's rewrite 20 as 4 times 5. Then we need to look at x cubed and ask, is x cubed a perfect square? It is not. If you look at our list of perfect squares, you won't see x cubed on that list. Remember, a variable will be a perfect square if its exponent is a multiple of 2. 3 is not a multiple of 2, so this is not a perfect square. The largest perfect square that multiplies evenly into x cubed is x squared. So let's rewrite x cubed as x squared times x. X squared times x is equivalent to x cubed because if you add the exponents, 2 plus 1 will give us 3. Now, once you've identified your perfect squares, you want to write them as some quantity squared. So I've rewritten 4 as 2 squared, and x squared is already perfectly written as some quantity squared. We can now pull those perfect squares out of the square root. So let's start by writing the coefficient 2, and then let's pull this 2 out of the radical, and we'll multiply it by that coefficient. And then let's also pull the x out of the radical. Now, all that we're left with underneath the square root is the 5 and the x. And now we can simplify this because 2 times 2 times x is equal to 4x. Now, all we've done in step 1 is just focus on this radical in the denominator and simplify it. Now I notice we can simplify a little bit more in step 1. There's an x in the numerator and an x in the denominator, so let's cancel, and that will leave us with 5 over 4 square root of 5x. Now we've completed step 1. We've simplified as much as we can. In step 2, we're going to multiply to get rid of this square root in the denominator. I'm going to start by copying this exact expression over here. And to get rid of this square root in the denominator, we're going to multiply the numerator and the denominator by this exact square root. And we don't need to include the coefficient. So I'm going to multiply the denominator by the square root of 5x and the numerator by the square root of 5x. That will leave us with 5 times the square root of 5x in the numerator, and in the denominator, there's no other coefficient to multiply the 4 by, so we'll leave the 4, but we multiply the radicals. The square root of 5x times the square root of 5x is just 5x. Now, I notice that we have a 5 in the numerator and a 5 in the denominator, so let's just cancel those 5's, and that leaves us with the square root of 5x divided by 4. Now we've rationalized the denominator, and for step 3, you just want to see if you can simplify your final answer any further. But nothing can be simplified further here. So this is our final fully simplified answer. Let's take a look at one last similar example. Now again, to rationalize this denominator, some people like to right away multiply the numerator and the denominator by the square root that they see in the denominator. And that works. You'll get the correct answer. But I always like to first, in step 1, simplify, because that will make your numbers smaller and often easier to deal with. So instead of doing this, let's simplify any radicals if possible. I'm going to start by copying the original problem here. 126 is not a perfect square. So we need to find the largest perfect square that multiplies evenly into 126, and that would be 9. So let's rewrite 126 as 9 times 14. Then let's look at the denominator. A to the 5th is not a perfect square. I know it's not a perfect square because the exponent 5 is not a multiple of 2. Here's the list of perfect squares that we made in our 6.3 worksheet. Remember, to find the largest perfect square that multiplies evenly into a to the 5th, we want to look at our list of perfect squares and find the exponent as close to 5 as we can get, but it has to be less than 5. That exponent would be 4. So the largest perfect square that multiplies evenly into a to the 5th would be a to the 4th. So let's rewrite a to the 5th as a to the 4th times some quantity. And let's see, a to the 4th times a is equal to a to the 5th, since when we add the exponents, 4 plus 1 gives us 5. Now, we need to write these perfect squares as some quantity squared. The perfect square 9 can be written as 3 squared. And let's write this perfect square a to the 4th as some quantity squared. Let's see. Remember, our rules of exponents tell us that when we raise an exponent to an exponent, we multiply. So we must put a 2 here because 2 times 2 gives us 4. Now, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So in the numerator, I pulled the 3 out of the radical, and in the denominator, I pulled the a squared out of the radical. And remember, the square root cancels this exponent too, leaving us with just a squared. Now we've completed step 1. We've simplified the radical in the numerator, and we've simplified the radical in the denominator. For step 2, I'm going to start by copying this expression over here. Now again, in step 2, we're rationalizing the denominator. And to get rid of this square root in the denominator, we need to multiply the numerator and the denominator by this exact square root we see in the denominator. So we're going to be multiplying the numerator and the denominator by the square root of a. And let's see, in the numerator, there's no coefficient to multiply this 3 by, so we'll just bring over the 3. The product property of radicals says that when we're multiplying the square root of 14 times the square root of a, we can combine that multiplication underneath one radical symbol to give us the square root of 14 times a. And then in the denominator, remember, when you're multiplying, you multiply coefficients and you multiply radicals. There's no other coefficient here, so we'll just bring over the a squared. But we multiply these radicals. The square root of a times the square root of a is just a. And so in the numerator, we'll have 3 square root of 14a. And in the denominator, when we're multiplying a squared times a, we keep the base and add the exponents. 2 plus 1 will give us a cubed. So we've completed step 2. We've rationalized the denominator, meaning that we've written the problem so that there is no square root in the denominator. For step 3, you want to check to see if you can simplify your answer any further, but this answer cannot be simplified any further. So this is our final, fully simplified answer. The last type of problem that we're going to look at is a problem like this. We're going to find that the technique we used on the previous pages will not work for a problem like this. I'm going to copy this exact problem on a separate sheet of paper so that I can show you how our previous technique will not work. In the previous problems that we've worked through to rationalize the denominator, we first checked to see if any of the radicals can be simplified. The square root of 5 cannot be simplified. Then we multiply the numerator and the denominator by the radical that appears in the denominator. So let's try that. I've multiplied the numerator and the denominator by this exact radical that I see in the denominator. And now I'm going to add parentheses here because we want to make sure that we're multiplying this whole denominator by the square root of 5. Now let's see. In the numerator, we'll have 8 times the square root of 5. And in the denominator, we're going to need to distribute this square root of 5 to each of the pieces inside the parentheses. The square root of 5 times the square root of 5 will just give us 5. And then we can take the square root of 5 times 1, which will just give us a positive square root of 5. Now notice here, the whole goal of multiplying the numerator and the denominator by the square root of 5 was to get rid of the square root in the denominator. But it didn't work here. We still have a square root in the denominator. This technique will not work if you're trying to rationalize a denominator that has 2 terms. Remember, a term is a quantity separated by an addition or subtraction symbol. So in other words, if you have 2 quantities in your denominator separated by an addition or subtraction symbol, this technique will not help you to rationalize the denominator. So this is the exact problem that we were just looking at. The technique that we've used on the previous pages will not work here. So how do we rationalize this denominator? To rationalize a denominator that contains 2 terms involving a square root, we multiply the numerator and denominator by the conjugate of the denominator. How do you find the conjugate of the denominator? All you have to do is change the sign in the middle of the 2 terms in the denominator. So let's look at some examples. How would you find the conjugate of this expression here? To find the conjugate, all you have to do is copy down this exact expression, but change the sign in the middle. That will give us the square root of 6 plus 2. Notice, when your expressions involve 2 terms and they look identical, but one has a minus sign in the middle and the other has a plus sign in the middle, we call those expressions conjugates. To find the conjugate of this expression, we just copy it down exactly, but we change the sign in the middle. That will give us the square root of 5 minus the square root of 3. To find the conjugate of this expression, we just copy it down exactly, but we change the sign in the middle. So that will give us 7 minus the square root of 2. To find the conjugate of this expression, we copy it down exactly, but we change the sign in the middle. Notice we didn't change this sign. When you're making conjugates, you only change the sign in the middle. Now let's take a look at this problem here. To rationalize a denominator that contains 2 terms involving a square root, we need to identify the conjugate of the denominator. To find the conjugate of this denominator, we just copy it down exactly, but we change the sign in the middle. That will give us the square root of 5 minus 1. Now, I've started by copying this exact original problem right here. To rationalize this denominator, we need to multiply the numerator and the denominator by the conjugate of this denominator. And here's the conjugate right here. So we're going to multiply the denominator by the conjugate, which is the square root of 5 minus 1. And we also multiply the numerator by the conjugate. And I'm going to add parentheses around this denominator because we need to make sure that we're multiplying this whole denominator by the conjugate. Now I'm just going to rewrite this expression by taking 8 times the square root of 5 minus 1, which I've written here, and then in the denominator I'm just going to take this quantity times this quantity, which I've written here. Now let's focus on the numerator and denominator separately. You might be tempted to distribute the 8 in the numerator, and you can do that and you'll get the correct answer in the end. But it's easiest if you do not distribute the numerator. I'm going to recommend you leave the numerator exactly as is. Don't bother distributing because it's going to be easier to simplify in the end if you do not distribute. Now, while I recommend that you leave the numerator exactly as is, we cannot leave the denominator as is because the whole goal of this problem is to rationalize the denominator. The denominator has square roots. We've not yet gotten rid of them, so we need to focus on simplifying this denominator in order to get rid of those square roots. And there are two different approaches we can take to simplify this denominator. One approach is that we can FOIL the denominator. I'm going to walk you through this approach first. I've started by copying this exact expression right here, but I've highlighted the denominator because we're going to be FOILing the denominator. To start, I'm going to copy this exact numerator right here because remember, I recommend you leave the numerator as is, don't bother distributing the 8. Now let's FOIL the denominator. To FOIL, we'll multiply the first, so we'll take the square root of 5 times the square root of 5, which will give us 5. Then we'll multiply the outer, so we'll take the square root of 5 times -1, which will give us negative square root of 5. Then we'll multiply the inner. 1 times the square root of 5 will give us a positive square root of 5. And then we'll multiply the last. 1 times -1 will give us -1. Now, notice we have negative square root of 5 plus the square root of 5. Those are opposites, so they cancel. And in the denominator, 5 minus 1 will give us 4. Now we've successfully rationalized the denominator by multiplying the numerator and the denominator by the conjugate of the denominator and then simplifying the denominator by FOILing. We've gotten rid of the square root in the denominator. Now the last step in any math problem is always to check to see if you can simplify it any further. Notice 8 divided by 4 gives us 2, so that will simplify to 2 times the square root of 5 minus 1. You can leave the final answer in factored form like this. If you'd like to take an extra step and distribute the 2, you can, and your answer would be correct. So we could take 2 times the square root of 5 to give us 2 square root of 5, and 2 times -1 will give us -2. So either this answer or this answer is acceptable. Now, we saw that we can simplify this denominator by FOILing, but there is another approach we could have used to simplify this denominator. We could have instead used the difference of two squares formula. And let me quick review the difference of two squares formula on a separate sheet of paper. We've learned that when you have two sets of parentheses that look identical, but one has a plus and one has a minus sign, you can use the difference of two squares formula. Now, notice these are conjugates. Conjugates are simply expressions involving two terms, and the expressions must look identical, but one will have a plus and the other will have a minus sign. So we've actually been working with conjugates all along, we just haven't yet introduced the vocabulary term conjugates. So anytime you're multiplying conjugates, you can use the difference of two squares formula. And the difference of two squares formula says take this first term and square it, and then take this second term and square it, and put a minus sign in the middle. And this will simplify to x squared minus 16. Now, we could have also FOILed this out and we'd end up with this exact same answer in the end. So remember, anytime you're multiplying conjugates, you can FOIL or you can use the difference of two squares formula. So I'm going to start by copying down this expression right here, and I've highlighted the denominator because we're going to focus on simplifying this denominator. Remember, we're going to leave the numerator as is because it's easier if we don't distribute the numerator. Now, since in the denominator we're multiplying conjugates, we can use the difference of two squares formula. To use the difference of two squares formula in the denominator here, we're going to take this first term and square it. So we'll take the square root of 5 and square it. And then we're going to take this second term and square it. So we'll take 1 and square it. And then we put a minus sign in the middle. Now we just need to simplify this denominator. If we take the square root of 5 squared, the square and the square root are inverse operations. They cancel each other out, leaving us with just 5. Or another way to think of this is that the square root of 5 squared is just equal to the square root of 5 times the square root of 5. And we know that the square root of 5 times the square root of 5 is just 5. And then we're going to subtract 1 squared. 1 squared is just 1. And 5 minus 1 will give us 4. And then just like we did over here, we can take 8 divided by 4 to give us 2. And then we'll bring down this square root of 5 minus 1. Notice we got the exact same answer over here. And just like we said over here, if you'd like to distribute this 2, you can. That will give you this answer here. Either answer will be accepted. Now, I suggested that you do not distribute the numerator because I think it's easier to simplify in the end if you don't distribute the numerator. But let me show you how to solve the problem if you do choose to distribute the numerator. So I'm going to copy this exact expression over here. If you decide to distribute the numerator, 8 times the square root of 5 will give us 8 square root of 5, and 8 times negative 1 will give us negative 8. Then for the denominator, you'll either want to FOIL like we did over here, or use the difference of two squares formula like we did over here. Either way, whether you FOIL the denominator or use the difference of two squares formula, you'll end up with 4. Now, if you did distribute in the numerator like we did here, to simplify, I would recommend splitting this, and I'll show you what I mean. We're going to write this as 8 square root of 5 over 4, and then we put the subtraction sign in the middle, and then we'll write this as 8 divided by 4. Now that we've split this, we want to simplify each piece. 8 divided by 4 gives us 2, leaving us with 2 square root of 5. We'll bring down the subtraction sign, and 8 divided by 4 leaves us with 2. So you can see, if you do distribute in the numerator, you can still get the same exact answer in the end, but you just have to remember to split it apart into two separate pieces. Let's take a look at one last example involving conjugates together. For this problem, we want to rationalize the denominator. And if you notice that your denominator involves two terms, in other words, you see two quantities separated by an addition or subtraction sign, in order to rationalize the denominator, we need to find the conjugate of the denominator. To find the conjugate of this denominator, all we need to do is copy down this exact expression, but change the sign in the middle. That will leave us with 6 square root of 7. We'll change that to a plus sign, 7 square root of 6. Now that we've identified the conjugate, I'm going to copy this exact expression down here. And to rationalize this denominator, we need to multiply the numerator and the denominator by this conjugate of the denominator. So I've multiplied the numerator by the conjugate and the denominator by this conjugate. And we need to add parentheses around this denominator to make sure that we're multiplying the whole denominator by the conjugate. Now I'm going to rewrite the numerator in one line and the denominator in one line. Now, remember, you can distribute in the numerator if you'd like, but most find that it's easier if you do not distribute the numerator. So I'm going to leave the numerator exactly as is, but we cannot leave the denominator as is because the whole goal of this problem is to rationalize the denominator, and the denominator is not rationalized. We have lots of square roots in the denominator, so we need to work on simplifying this denominator. And we have two different options. We could FOIL this denominator, or remember, whenever you're multiplying two conjugates, you can always use the difference of two squares formula. You can pick whichever approach you prefer. For this example, I'm going to use the difference of two squares formula. And I've highlighted the denominator because that's what we're focusing on. We're going to apply the difference of two squares formula to the denominator. I'm going to copy this exact numerator down here because we're leaving the numerator as is. Now, to use the difference of two squares formula for the denominator, we start by copying down this exact term, 6 square root of 7, and we square it. And then we copy down this exact term, 7 square root of 6, and we square it. And then we put a minus sign in the middle. That's why it's called the difference of two squares formula, because you're subtracting two squares. Now I'm going to continue copying down the numerator as is. And to simplify this, we can apply the square to the 6, giving us 6 squared. And we can apply the square to the square root of 7, giving us square root of 7 squared. And same thing here, we can apply the square to the 7, giving us 7 squared. And we can apply the square to the square root of 6, giving us square root of 6 squared. And I'll continue copying down this exact numerator as is. 6 squared will give us 36. And to compute the square root of 7 squared, we can think of it as the square root and the square being inverse operations, so they cancel, and that will leave us with just 7. Another way to think of this is that the square root of 7 squared is just the square root of 7 times the square root of 7, which gives us 7. Then 7 squared will give us 49, and the square root of 6 squared, the square exponent cancels the square root, leaving us with just 6. Or again, we could think of this as the square root of 6 times the square root of 6, which gives us 6. 36 times 7 will give us 252, and negative 49 times 6 will give us negative 294. 252 minus 294 will give us negative 42. And now we've successfully rationalized the denominator because we've gotten rid of the square root in the denominator. And now to write our final answer, we need to look at this answer and ask ourselves, can we simplify it any further? We can, because we can take 84 divided by negative 42 to get negative 2. And then we'll carry down this expression here. Now again, you can stop here leaving your answer in factored form, but if you'd like to take an extra step and distribute this negative 2, you can. If we distribute negative 2 to 6 square root of 7, that will give us negative 12 square root of 7. And negative 2 times 7 square root of 6 will give us a negative 14 square root of 6. So either one of these final answers is correct. And if you prefer to FOIL the denominator instead of using the difference of two squares formula, you'll end up with the same exact answer in the end.